Good afternoon, everyone. It's almost the end of the day, so we're almost there. But it's a great pleasure to be presenting our work in this amazing conference. My name is Konstantina Vlahu, and I'm the Heritage Science Manager at Historic Royal Palaces. And today I'm going to talk about historic tapestries and how a series of studies helped us to understand the mechanical properties and their response to the environmental changes that provided us crucial information for their protection. So for those who are not familiar with our organization, Historic Royal Palaces is a charity that administers 6 historic sites in the United Kingdom, including Hampton Court Palace, which was the home of Henry VIII, and he was a great collector of historic tapestries. Today, in our collection, we have 70 tapestries, while 40 of them are from the Tudor period. Tapestry conservation has also a long presence in Hampton Court Palace, as our studio was established by William Morris over 100 years ago. So, of course, it's not a surprise that the study of these intricate textiles has been one of our primary areas of research over the last 20 years. And here you can see the evolution of this research with several back-to-back projects. However, today we'll focus only on 3 of them. So the first project was a doctorate collaborative partnership with the University of Manchester, which started back in 2009. During her research, our PhD student Philippa Dufus started the structural integrity of historic tapestries. The second project that we will discuss today is the Tudor Tapestries Environmental Protection. That was an in-house project funded by Historic Royal Palaces. And during this project, we explored the impact of environmental risks on the Tudor tapestries in the Great Hall at Hampton Court Palace. The third project, Modeling Strain in Historic Tapestries, was another doctorate research in collaboration with University College London and IBM Research, which was funded by SIHA, Center for Doctoral Training, and Pedro Rocha was our PhD student. So over the next 15 minutes, I'll try to summarize 15 years of research, so bear with me. And I will organize our work and the results under 3 main areas: the physical and mechanical properties of historic tapestries, the impact of the environment and the changes of the environment on them, and also some attempts we had to model and create some digital twins of historic tapestries. At the end, I hope to sum up some of the key points of our research and suggest some future work. So before we proceed, of course, let's remind ourselves what is a tapestry. As we mentioned, I think it was happened in the first day that he mentioned what the properties of a tapestry. But again, let's explain. So it's a weft face textile, which means that the colored threads, the weft, interweave and entirely cover the supporting plain threads, the warp. The weft threads carry the pictorial design as well as forming part of the physical structure of the textile. And most importantly, this is the direction that the tapestry hangs when open display. So let's now proceed on the experimental work. Philip, our first student, prepared 2 types of model samples. The one had wool weft and the other one silk, while both of them they had the wool warp. These samples were exposed to humidity and thermal aging, using an environmental chamber where 10 samples were placed on a rack, they were relaxing, and the other 10 were hanging under strain from weights, as you can see in the image. The details of the environmental cycles and the style testing are also in the slide, and I don't have time to explain, but we can go back if you have questions. So let's proceed on the results. So the figure on the left shows the tensile testing results of wool weft fabric after 100 and 170 and 240 cycles, showing that the higher the number of cycles, the higher the loss in fabric strength and extensibility. The stiffness of the fabric also increased, as indicated by the increase in gradient in the elastic region of the graph. The results, however, of the silk wool samples on the right indicate that the effect of RH aging was slower, with a first significant decrease in strength observed in 240 cycles. Also, when we look at the stiffness, silk weft samples showed contrasting behavior to the wool ones. So this potentially could be attributed to chemical variations, as silk degradation causes breaking of the peptide bonds, converting a larger portion of the fiber into an amorphous region, which is less stiff. However, for the wool fibers, the primary effect of aging is that the disulfide bonds are converted to rigid cross-links, which effectively lock the fiber structure in its place, so it's making it more difficult to extend. So tensile testing results of the aged samples under strain compared to the ones which placed on the rack are shown on this graph. Blue indicates samples with wool weft and green samples with silk. The dotted lines represent the results of the samples that aged under strain, and they demonstrate clearly that they experience significant increase in stiffness. This is an important observation, as many tapestry collections are hanging under the strain of their own weight for a long period of time. As part of Philippa's project, we had the opportunity for the first time to perform tensile testing in 10 historic samples. So the figure on the left shows the comparison of historic and light aging fabric, which suggests that the historic samples, you can see there the tiny line, they were much weaker than the artificially aged ones. The graph on the right shows the tensile testing results of the aged replica samples in full line and the historic tapestry fragments, the dotted lines, in both weft and warp directions, indicating that the weft on the historic samples was considerably weaker following long-standing degradation. So the 10 fragments Philippa used in her research were selected from the Historic Tapestry Archive we're fortunate to have in the HRP's Heritage Science Lab. Pedro, our next PhD student, also selected 33 samples from this archive for his research. And he performed a range of techniques to record their physical properties and also deployed tensile testing with DAC to measure their mechanical properties. And here you can see the tensile testing setup on the right, and on the right experimental parameters. During tensile testing, a camera was recording a set of pictures at each 1 millimeter extension, and these images were then used for the DAC. Pedro tested initially a uniform wool samples to failure, so that was a historic sample. And here you can see the stress-strain curves of 2 different sample areas from these fragments and their characteristics. The DAC measurements calculated during the experiment show that when the sample is under strain, under tension, strain in the vertical direction, which is the bottom left image, is positive as the fabric is stretching, while the horizontal, the image on the right, is mostly negative due to shrinkage. And here are the all the progressive images of this experiment until failure. So if we focus on the initial stages of the test, we can see that the area with a slight change in the width has been highlighted in the DIC analysis, and this was the area eventually that was failed. So this is very interesting result because even in a very uniform fragment, a very small difference in the weft structure can produce significant change in strain, and that can result in failure after long exposure in changes. On the right, you can see a 3D model Petro prepared with a fabric after failure to show the 3D effect. And here, you can see the results of the tensile testing of the 33 historic fragments. 3 areas of each of these fragments were tested until 11% strain, and the figure shows the average of each fragment. The blue lines represent wool, the red silk, while yellow indicates mixed areas. So these stress-strain curves show that the 3 homogeneous wool fragments were generally stiffer than the homogeneous silk fragments. And that outcome was in line with Philippa's experimental results we discussed earlier. However, for mixed or non-uniform wool fragments, the results were not as consistent, most likely due to the complex structure or presence of slits. So to study the potential impact of fatigue in areas with design changes and stitched slits, 2 historic fragments were tensile testing in the same area. So in the slide, you can see the stress-strain curves until 7% strain for 5 tensile tests on the left and the DIC images on the right. The results from the fragment on the top show little change following 5 vertical strain repetitions. However, the fragment 32, which is at the bottom, the stress-strain curves become consequently less stiff, as DIC map shows increased strain in areas where the stitched slits become more loose and open up. So again, quite interesting information about the behavior that our tapestries experience when when they're under strain from their weight. So let's talk now about how we monitor the impact of the environmental changes on the tapestries. As part of the Tudor Tapestries environmental protection, we were particularly interested to understand how the tapestries responded to the daily environmental changes we had in the Great Hall at Hampton Court Palace. To do that, we used a laser sensor, which we positioned it at the bottom of the tapestry, and the laser was tracking the changes on the heights, the distance between the sensor and the edge of the tapestry. In the graph, the blue line shows RH data, and the red line, the data from the laser sensor. And you can see how very clearly the tapestry responds to the daily environmental fluctuations over a period of 25 days. And during that period, in the palace, we were turning off the heating at night and turning it back on during the morning. So you can see how these fluctuations were affecting directly our tapestries. To take this work further, we partnered with IBM Research using their novel sensors, which measured also distance changes. But this time, as these sensors are very small, we were able to install a number of them across the full height and across the edge of the tapestry at the bottom to assess the strain distribution across these areas. And these novel magnetic sensors were detecting relative motion between the chip and the magnet. And here you can see the magnets on the surface of the tapestry, which were almost invisible. The graph on the right shows the results from the sensors positioned on 3 different heights, with dark blue at the highest point, pink in the middle, and yellow at the bottom. And again, we can see that the response is directly correlated to the position, so that the highest point moved the least, while the lowest had the most movement. Following on from this work, as part of Pedro's research project, we purchased a small 19th century tapestry to perform hygroscopic tests in an environmental chamber. The response of the tapestry was measured using IBM sensors, which are highlighted in blue in the image, and also a 2-camera stereoscopic DIC system was set up and calibrated to record the area you can see again on the slide. Okay, now this has a lot of explanation. So the experiment involved 4 environmental cycles with RH changes between 40 to 80%, with a period of a fixed soak at each extreme and a stable temperature. We repeated the same set of experiments for a 15 degrees centigrade temperature and another one for 25 degrees centigrade. The top graph shows the RH, absolute RH and temperature graphs for the cycle at 15 degrees centigrade. However, for this set of temperature, the chamber could reach only the lowest point was for 55%. So for 15 degrees centigrade, the RH was changing from 55 to 80%, just to note. So in the lower graph, we can see the strain calculations from the DIC with a vertical strain in yellow and the horizontal in black. These results indicate that strain changes match the changes in RH and absolute RH. The vertical strain is more affected by changes in moisture than the horizontal strain, potentially due to perhaps the increase of tapestry's weight because of the exchange with the moisture. In the vertical strain, increases of approximately 0.15% were observed in all cycles when RH changed from 55 to 80. Changes of almost the same magnitude, but with a negative sign, were observed when we had the change back to 55 degrees. Results from the experiment at 25 degrees centigrade showed higher strain variation compared to the 15 degrees. RH increased from 40 to 80%, caused 0.3% vertical strain, while when the level of RH drops back to 40, the vertical strains around 0.2%. For the horizontal strain, an increase of around 0.2% is observed when RH changes from 40 to 80, and when returns back to 40, it was less than 0.1%. So the changes in the strain the tapestry experienced between 15 degrees and 25 degrees temperature potentially could be interpreted by looking at the variations in absolute humidity. At 15 degrees, Pedro calculated that absolute humidity increases from 7 grams per cubic meter to around 10, while when the temperature is set to 25 degrees, it changes from around 9 grams per cubic meter to 18. So for the same levels of RH, when the temperature is higher, the air contains more moisture, and potentially the tapestry fibers absorb a higher amount of water, which causes more strain. Originally, we were planned to install load cells on the top of the tapestry to measure also the weight changes. However, this didn't materialize because of COVID. So that, unfortunately, we don't have this set of data to compare. And now, very briefly, let's see the results from the IBM sensors. A rise in moisture means a decrease in the distance of the magnets and receptor as tapestry expands. However, for direct comparison with the DIC results, we reverse the sign from the results of the IBM sensors to so you can read them more easily. So for the 15 degrees centigrade, the measurements followed similar behavioral patterns as with vertical strain DIC results. In terms of magnitude, there is a change of around 0.05 millimeters as the level of RH increased from 55 to 80%. However, for the cycle at 25 degrees, the displacement increased to 0.1 millimeter. And that, again, was in line with the DIC results, and potentially we can explain it with because of the absolute humidity changes. In both experiments, although most of the sensors tend to follow the same pattern, some of the displacements are slightly different, potentially due to the design differences on the tapestry. So now, very briefly, I'm going to talk about the modeling, because I'm running out of time. So Philippa, as part of her project, developed an initial model for a tapestry using FEM methodologies, and these figures, they represent the tapestry 6 meters width to 4 meters high. The tapestry is constrained across top level, and we can see on both edges, on the top corners, there is strain building up. The middle figure shows the development of slits, and again, how they behave when we apply gravitational load. And the figure on the right shows the material slightly changed and aged. And on that case, the slits opened up a bit more, indicating that when we have a force that is greater, then we have more effect in the inherent structural faults of the tapestry. And Pedro also, in his research, he did follow on Philippa's methodology and created another model. This time we used the size of an Abraham tapestry. It's almost 8.5 to 5 meters. And also we had 3 holes that represent the slits. Also, he used some of the data from the tapestry fragments to fine-tune a bit better this model, and he simulated the hanging mechanisms of a tapestry. So the top one is the nails that they used to hang the tapestries historically, while the bottom one is the Velcro. And again, you can see the distribution of strain. So I think I need to finish. So very briefly, to sum up that one of the main outcomes of our research has been the detailed characterization of mechanical properties of replica, as well as historic tapestry samples. So that was very important for us, that we were able to incorporate some real samples in our studies. Also, the fact that we have experimental evidence that the strain the tapestries experience under their own weight contributes to the degradation. Overall, the results suggested that the strain in tapestries adapts closely to the environmental changes, indicating that the fibers quickly absorb and dissolve water. The structural features, such as the weave interruptions and the presence of slits, have a significant impact on the tensile properties of the tapestries. Potentially, DAC can be used in the future as a technique that can identify areas that they, in the future, they might suffer from more damage. And of course, fair modeling we have initiated this work, but we need to progress further. So in the future, we hope to incorporate the mechanical characteristics and the hygroscopic response data we developed from Petros project. And also we hope to have a digital twin that we can interrogate and see if we can test the conservation strategies our textile conservators apply to support the tapestries when they're on display. So this is a list of, wrong. This is a list of publications from the projects I have just discussed. And of course, I would like to acknowledge our PhD students and our academic and industrial collaborators and colleagues at Historic Royal Palaces that supported this work. So thank you.
Is there any question? Just one.
Thanks, Konstantina. Really interesting, and I just wonder, in relation to tapestries and the history and production of the tapestries, whether or not you see, well, first of all, do you know the production of the tapestries in terms of high warp or low warp looms? And do you see any of that playing out in the results across the board, or is it just you don't have that information to determine how it was originally produced?
It's not very easy to define that. However, when we picked up the samples from our historic archive, we tried to have a representative range of the qualities of tapestries in terms of their thickness and the design. So that Petro, when we did this selection of the 33 samples, we try to be as representative as possible of the different variations.
Thank you, Konstantina.
Great, thank you.